Right now we have a really great talk by Adrian Herrera on program analysis for reverse engineers from top to bottom. So let's welcome Adrian to the stage.
Thank you. Can you all hear me all good? All right. So yeah, so that last talk was really great. And hopefully we can sort of continue on that reverse engineering theme. But I don't know, depending on how you feel about this, my aim is kind of to add a bit more maths to it. So hopefully you're all like some maths like I do. And so yeah, so the focus of this talk will be how do we use some research from the formal methods, mathematical world, and how we apply that to reverse engineering. All right, so who am I? My name's Adrian. I'm a researcher with the Defence Science and Technology group here in Australia. I'm also a visiting researcher at ANU, and I guess my day job is building these tools, looking at this idea of how do we take this academic work on program analysis and apply it to reverse engineering problems. So that's what I really like doing. All right, so I'll cover a bunch of different things in this talk. Lots of different, so program analysis is a massive field. I guess it's been a research field in academia for forever, so I can't talk about all of it, but I've picked sort of three what I think are really useful areas that can be applied to reverse engineering. And that's looking at Smt Solvers, Symbolic Execution, and abstract interpretation. All right, so what is program analysis? Program analysis is pretty broad, so the definition is kind of a bit wishy-washy and probably doesn't mean anything, but it's basically how do we build tools to reason about other programs' behavior. As I sort of just said, it's been a research field, active research field for decades, primarily in the compiler field, but I think quite recently with DARPA's Cyber Grand Challenge that they held maybe 1 or 2 years ago, a lot of these concepts from the compiler space are making their way into the security space, and that's kind of what I'll talk about today. So program analysis is automatically reasoning about computer programs and what they do. So what kind of things do we want to reason about here? Well, I've listed a few up here. Security, correctness, and yeah, compilers are some of the common things that we want to reason about in our programs. All right, so in program analysis, there's kind of like two main flavors. If you're a reverse engineer, you're probably already familiar with these terms anyway, and we kind of brushed up on this in the last talk, but you can either analyze something statically or you can analyze something dynamically. And the difference is basically when you do dynamic analysis, you execute the program and you reason about a particular execution trace, whereas with static analysis, you reason about the program without actually executing it. Whoop, wrong button. All right, so what are the pros and cons of this? Well, so with static analysis, we get a broader overview of what our program is doing. So we can reason about in theory, we can reason about all execution traces through the program. But as we'll come up a bit later on when we talk about abstract interpretation, this is not actually possible due to some theoretical reasons in computer science. And so in contrast, dynamic analysis, we can only reason about what we see, right? So in the previous talk, we talked about, Richard talked about instrumenting the Ruby VM. And so we can only sort of generate and reason about the traces that we actually get for a given input. So an example of this in fuzzing is we have to generate lots and lots and lots of random inputs and feed them to our program to try and uncover many different code paths through the binary. But the upside of this is that because we get a complete execution trace, we can be more precise about what we're reasoning about. And so yeah, so if you're a reverse engineer, you probably already use tools that do some form of program analysis. So if you do static analysis with IDA Pro, you load your binary in IDA, it gets disassembled, A control flow graph gets reconstructed. You might get some like type inference information that IDA can maybe or maybe not figure out, depending on how obfuscated your binary is. And all of this, jump table recovery as well, all of this is, I think, falls under the umbrella of program analysis. In contrast with dynamic analysis, if you're a malware person and you use a tool like Cuckoo Sandbox, you inject a DLL into your malware, you run it through Cuckoo, you generate traces, and then you can sort of reason about the behavior of those traces. And so with malware, maybe you're interested in API monitoring, and with fuzzing, maybe you're interested in code coverage. And again, I would argue that that all falls under program analysis. All right, so program analysis in academia is kind of a disgusting thing, I think. So this is kind of like the paper that introduced abstract interpretation, and it's completely incomprehensible. I have no idea what any of it kind of means. And so I'm hoping with this talk, we can sort of avoid this garbage and, well, I shouldn't call it garbage, this stuff, and talk about it in a more practical sense for reverse engineers. All right, so what are my aims here? I kind of want to talk about new, maybe possibly unfamiliar program analysis techniques, so not really focus on control flow graph generation and that kind of thing. Gear it towards reverse engineers, have a ton of examples, try and limit the maths like we saw in that previous slide. I'm sort of not going to dive into code or anything like that. I sort of just want to talk about the ideas behind these different techniques. And we won't focus on any specific instruction set architecture, and that's mainly because that's hard, right? So something like x86 has hundreds and hundreds of instructions, and trying to write programs that reason about those hundreds and hundreds of instructions is really, really difficult. And so instead, what we'll talk about is we'll sort of talk about program analysis on top of intermediate representation, which is quite common anyway. And the one I'll focus on is this one, Rail. That was developed by now Google people, and it's a very simple intermediate language for assembly code. And so, all the examples that I talk about will focus on this IR. All right, so a bit about Rail before we sort of dive into some analysis. Yep, it was developed by Dynamics, who are now at Google. If you've ever used BinNavi before, you can export your code to this Rail intermediate language, and it's very simple, and it was designed to be very simple. So there's only 17 instructions in the entire set. All instructions take 3 operands, some of them may be unused, and I think the most important thing for Rail is that there are no implicit side effects. So when you execute an instruction, say on x86, maybe you're doing an add, as well as getting a result of that addition, you also set flags. Maybe the result is 0, so you set the 0 flag. Maybe you get an overflow, and there are all these implicit side effects that happen kind of behind the scenes, and this complicates your analysis, right? Because you have to reason about all these possible side effects that can happen. So the nice thing about Rail is, for an addition, it just adds 2 numbers, right? It doesn't set any flags. You have to explicitly generate instructions for it to do that. So this is an example of what Rail looks like. Yeah, it just looks like any old assembly language, I guess. We've got XORs, addition. This stir instruction is nothing to do with strings. It's a store to register. So it writes the value 20 to the register R2. And STM is store to memory. So it stores the value in R1 into this memory address. Yeah, and so that's kind of what Rail looks like. And so I think it's important that we kind of differentiate between the syntax of Rail and the semantics of Rail. So we kind of heard the word semantics a bit in the previous talk, which was really good. But I'll just kind of dive a bit deeper, I think, into what we actually mean by these 2 terms. So the syntax, if we're talking about languages, is the symbols that make up that language, while the semantics are the meaning behind those symbols. So what do they actually mean? And so when we do something in IDA Pro, we're kind of looking at the binary at a syntactic level, right? And we sort of have to reason about the semantics in our head when we're going over the C of G, or whatever it is that we're doing. And so in this case, our syntax are our various instructions, so XORs, additions, whatever, operand sizes, registers, integer literals, that sort of thing. So when we, write a parser, we parse syntax, right? And we generate these things here on the left. So in contrast, when we talk about semantics, we're talking about, well, what does it actually mean to do an add? And so, as I said, the nice thing about Rail is that it's very obvious what these instructions do. So an add, in this case, we look up the value from R1, we add 10 to it, and we store the result in R1. And that's it. That's the meaning of add. And yeah, so if we were talking about an x86 add, then we would also have, well, if the result is 0, then we set the 0 flag, sign bits, and all of that sort of thing. All right, cool. So let's dive into the first sort of area, and that is Smt Solvers. All right, so I'll kind of switch to C for this example, but we'll get back to the assembly stuff later. So say we have this if statement in C. So it's based on 3 different variables, x, y, and z, and depending on some combination of x, y, and z, the if condition will be true, and we'll execute whatever code is inside there. So what we can do with this in the program analysis world is model this kind of code as maths. And when we do that, we can then use tools such as Smt Solvers to reason about these formulas for us and prove particular properties that we may be interested in. So this is what this C code looks like in logic land, and you can kind of see that it's pretty much a one-to-one mapping, except for we've got a couple of weird symbols in there. So we've got, this upside down V is an AND operation. This is just a NOT, and this is how we represent an OR. And so once we have this formula, we can do various things with it. So we can do just basic things, just assign values to X, Y, and Z, and then get a result. So if it's true, if it's false. We can give the formula to our Smt solver and say, and ask it, well, actually, is there a set of assignments for X, Y, and Z that will make this formula true? Yep, so that's checking satisfiability. And the other thing we may be interested in is if the formula is valid, so the validity of the formula. And what this means is that no matter what values we give to X, Y, and Z, the result will always be true. And so we'll see later on where this is kind of useful information. All right, so we'll just quickly do a simple assignment. It's pretty straightforward. So we'll just pick some values for X, Y, and Z, and then plug them in. And then we can sort of see 5 is greater than or equal to 3, so that'll go to true. We'll, expand this, expand all this stuff. So we rewrite our formula, we evaluate part of it. Now we've got some more funny symbols from the title, and so this T is top, and here it means true, and this other one is bottom, and it means false. So all we've done is just solve some of these comparisons here, like this one, 5 is greater than 3, that's true, and so on. And so we can sort of keep doing that until we get an end result. So false and true is just false. So is the formula valid? Well, clearly not, because we just gave a set of assignments for X, Y, and Z that didn't return true. So this formula is not valid. But we can ask the Smt solver, is the formula satisfiable? And it will say, yes, it is. And then you can say, well, give me values for X, Y, and Z that will make this true. And when I ran this with Smt solver, it gave me these values, 5, -2, and 5. And so, yeah, so in general, if we want to sort of model code as these logical formulas, this is kind of the approach that I would take. So the first thing we have to do is convert code to what is known as SSA form, static single assignment form. And basically what this means is that every variable in our code is assigned only once. And if we reassign that variable, we create a new variable. And I'll have an example that sort of walks through this. Once we have everything in SSA form, we can convert all our instructions into these formulas. And then we can AND all these formulas together and then give the resulting formula to the Smt solver and find out whatever information that we're interested in. So here we've got some Rail code. It's a bit more complex than the if statement that we just looked at before. So we can see we've got some XOR instructions, so clearing R1, and we're storing the result in R1, so things will have to change when we convert this to SSA form. We've got some additions, some multiplications, and then this one here in Rail is a conditional jump instruction. And so it works by if the first operand is not equal to 0, then we'll take the true path, we'll do the jump, and if it is 0, then we'll go the other way. And so inside all these registers, we've got these input registers that we control, and we can give values for. And what we want to work out is what value of in do we have to provide to go down these particular branches in our program. So the first thing we do is convert to SSA. And so how I've done that here is just appended these characters to the end of each register name. So remember the rules for SSA form are that you can only assign to a variable once. So that's why, on the previous slide, when we cleared R1 and assigned the result back to R1, we have to create a new variable now. And so likewise, when we read from R1, say down here, we have to update that to read from the newly created R1A. And there are some tools that will do this for you. So if you've used Binary Ninja before, it has an intermediate representation that has an SSA form. So you can kind of get this transformation for free if you use that tool. All right, so then once we've converted to SSA, we can sort of rewrite all our instructions as maths. And so this is kind of what it looks like. So R1A is just XOR. R2, we're just storing the -1 literal in R2. And we sort of do this for all our instructions here. And because we're interested in going down this path to this address here, this variable here must be equal to 0. So we add that in our constraint set. And so again, I guess this is where semantics becomes important. We can do this conversion from the Rail code to these formula really easily because the semantics of Rail are very simple. And so likewise, if we want to take this path, JCC means that we go down this path when this is not equal to 0. So we use not equal to 0 here instead. So as I said before, now we take the conjunction of all these formulas, so we AND them all together. This is the other one for the green path. And then we pass our formula to our Smt solver. And our Smt solver comes back and says, well, if you want to go down this path, then the input that we control must be equal to 0. And we can say, well, what other values for the input can we use to reach 14? And so to do this, we update our formula with the inverse of our previous result. So we say, well, to get to 14, we want all these to be true, and we don't want the input to be 0, because we've already got that solution, right? So we're not interested in getting it again. And we can keep doing that and iteratively generate new values for in that will take us down this path. Likewise, for this path, we give our formula to the Smt solver, and we say, is there a solution to this formula for the value for in that will get us down here? And we do that, and it actually tells us no. There is no solution there is no value for in that will take us down this path. And so what does this mean? So if you're a reverse engineer, or a malware analyst, I should say, maybe you've come across this term opaque predicate before, and basically what it is it's an obfuscation technique to fool reverse engineers into REing pointless code. So I can come up with some complicated code like this that looks like a really complicated branching condition, but in fact, it will always go down one particular path. So in this case, we'll always go down to address 14. And then I can put whatever code I want here and know that it will actually never be executed, but a reverse engineer may waste their time sort of REing all this code down here. And so if we use a technique like this, then we can sort of prove that actually there's no use reversing this code here because execution can never possibly get there. So that's kind of nice. So some applications of this, opaque predicate detection in the compiler space. If we're optimizing code and we find some code paths that actually there's no possible way we can execute them, we don't have to add those code paths into the binary. So that's another use. And there's a whole pile of research on automatic exploit generation and using these techniques to essentially represent your shellcode as these formulas and then finding paths to exploitable code and then seeing if it's actually possible to use your shellcode in that exploit. So this example was pretty straightforward. We didn't have any loops or anything like that. And if we do get loops, this is kind of where this breaks down. So if we know the loop bound, so we know the number of times that the loop iterates, we can unroll the loop and just generate larger formulas. But if we can't work out the loop bounds, maybe it's obfuscated in such a way that we can't, or maybe it's just an infinite loop, then we can't really use this technique in that case. And so some of the other issues with this, with Smt solvers, is even though they've improved a lot over the years, they still may not be able to solve really complex formulas. And so, they may just time out or give up and not give you a solution. As I said, if you're dealing with infinite loops, you can't really convert your code into a formula this way because you don't know how many times it will execute. So that's it for Smt solvers, and I think this leads nicely into symbolic execution, which is also Smt solver based. So previously we kind of looked at modeling code as these logic formulas, and so now what we'll do in symbolic execution is to run an interpreter over our code, generate these formulas dynamically, and then solve them as we're interpreting our code. So as far as all these kind of program analysis ideas go, I think symbolic execution is probably one of the more popular ones. There are tons of symbolic execution engines out there on GitHub that are all free and open source. Anger, this one here, is probably the most popular one, I would say. But there's others, Manticore and Klee, S2E, and there's a whole bunch of them that you can download and have a play with. So this is kind of a spiel on what symbolic execution is. I'm not really going to read through it. I think it's best just to go through an example, and then we can see how it works through that. But basically, instead of operating on concrete values, we operate on what we call symbolic values, and then when we operate on these symbolic values, we generate the formulas that I was just talking about. All right, so let's look at an example, slightly a bit more complicated than the last one. So now we've got two sort of different points that we can branch from. And what we'll do is we'll kind of just run this through our interpreter or our symbolic execution engine and generate the constraints required to take each particular program path through this CFG. So, down this path here, down this path here, and down that path there. All right, so we'll start. So again, we have our input that we control, and we'll make it symbolic. So we don't give it a particular value. We'll just give it this symbol for now, and everything else sort of stays as is. So we've still got like zeros here when we XOR these together, zeros here, and then we reach our first branch point. And so this instruction here is saying, well, if in is not equal to 0, we'll go this way. If it's equal to 0, we'll go that way. So we'll update our formula to say that. So maybe we want to explore this path first. And so to go down this way, this path, in must be equal to 0. And we add that to our set of path constraints. And then we sort of keep going. We update all this stuff. This is not operating on any symbolic data, so it doesn't change much. And then we get to here, and then we sort of exit our program, and then we go to our Smt solver and say, well, what are the values for our input that will take us down this particular path? And in this case, it's pretty straightforward. In must be equal to 0. So then we back up, and we look down our other path that we can take, and to go down this path, it's the opposite of going down this path, right? So now in must not be equal to 0. But now we're operating, now we've got some instructions that are operating on this symbolic data. So all we do is maintain this formula representation of what the results will be at the end when we pass it to our Smt solver. So yeah, so temp here, we're ending, our formula here with this, and then we're shifting it, and then we reach another fork point. And again, it's the same conditions. If this variable here is 0, we'll go down this way. So we update our path constraints for this branch point here, which was the input is not 0, and this branch point here, which is this complicated, ugly-looking thing. And we keep going. And then we get to the end, and we give our path constraints down here to the Smt solver, and it says, well, if in is equal to 1, it'll go down this path, and then maybe we want to generate other solutions for this, so it'll give us 2, 3, etc. And that's because what we're doing here is basically checking the sign. So these are all 32-bit integers, and we're checking the sign. And if the sign is 0, then we're going down this path. So it's a positive number. And then we back up to our last branch point, and we repeat the process. But now our constraint is that this value for temp is not equal to 0. And we keep going, and then we reach the end, and we say to our constraint solver, what do I need to go down this path? And it gives us these results. So that's kind of cool. So where is this stuff useful? So symbolic execution was originally designed for test case generation and software testing, but it's kind of now really heavily used in security tools and binary analysis stuff. So the DARPA challenge that they ran, out of all the finalists, I think there were 7 finalists in the competition, they all used a symbolic execution engine to do their automatic exploit generation. And they combine their symbolic execution engine with a fuzzing tool. And so this is useful because if you do fuzzing, you'll know that when you fuzz, you're kind of just doing things blindly, right? And you're just mutating different parts of the input in the hope of uncovering a new program path. But what we can do instead is we can be a bit smarter and generate these formulas and then invert them to get a solution that will take us down a new path that we haven't seen, and then sort of use that result as a seed for our fuzzer and switch back to fuzzing and sort of repeat this process. So it's good for improving that. And it has uses in malware analysis as well. So again, there was no loops in that example. What happens if we have loops? Well, bad things generally happen, actually. So we sort of, when you have loops, each time you iterate a loop, you generate a new path to explore. And if you have lots of if-else conditions in your loop, then you quickly get an intractable number of states to explore. And this is kind of, I think, the main downfall of symbolic execution. And there's a lot of research at the moment into how we can reduce this state space explosion problem, as it's known. And yeah, so this is kind of what stops symbolic execution from being really useful on large, complex binaries. So with the DARPA challenge, a lot of the programs that they were finding bugs in were these toy binaries that weren't overly complex. And so this technique kind of worked really well for that. And so yeah, so that's kind of the main challenge here. The other one that I've listed is this path selection. And what I mean by that is if you've generated all these forks in your program, you want to sort of pick the one to explore next, but you want to just not pick blindly, but sort of pick smartly so you can work out what you're interested in finding. If you're, for example, doing vulnerability research, you want to find a bug, so you want to sort of pick the next state to explore that you think will lead to some buggy code or something like that. All right, cool. Final topic is abstract interpretation. And so this is kind of different to the other two. So the other two, we sort of use Smt Solvers to reason about our code, and this is kind of completely different to that. So why do we want to use this abstract interpretation thing? It all comes down to Rice's theorem, which kind of says that any non-trivial property of a program is undecidable to prove and reason about. And so, well, you might think, well, what's the point then? Because, if all the interesting things we want to reason about in our programs are undecidable, well then we may as well just go home, right? And just stick to IDA Pro. But this is where abstract interpretation comes in. And so the way that it works is that it kind of works on an abstract layer that is now decidable. So we can now, if we abstract our program properties, we can now prove things about them that we couldn't prove about before. The downside of this is that we kind of lose some information as we'll see in the examples. All right, so yeah, so what we'll do with abstract interpretation is we'll take our semantics or our meaning of all our different instructions, and we'll abstract them to work on, I guess, a higher level to make the analysis possible. And so I kind of like to think of breaking down abstract interpretation into these three things that we need. We need a domain, we need an abstraction function, and we need some semantics. And then it's sort of, we combine all this stuff together, then we get an abstract interpreter. All right, so I'll go through each of those three things one by one, and then we'll look at an example. So with our domain, when we sort of do concrete executions, where we're reasoning about an infinitely large set of values, right? So, all the possible sets of integers or whatever. And so the key idea here is that we reduce what we're analyzing, we reduce the size of these sets so that we can approximate them in such a way that we can sort of still infer some meaningful information about our program. And so some common examples when you sort of read the literature on this stuff are sign domains and interval domains. And so what this means, so for the sign example, instead of looking at actual values of integers, 10, minus 10, 0, 1,000, whatever, we only look at their sign information. So, maybe we only care if a value is positive or negative or 0. And the same with intervals. So maybe we don't care about the precise value of an integer, we only care about the range of possible values that can hold. And when we do this abstraction, we can, it makes it easier for us to reason about. And so if you ever looked at abstract interpretation stuff, you always see lattice theory and all this disgustingness. And so I guess one of the rules, I don't know if you call it a rule, is that our abstract domains have to form a lattice. And so for our sign domain, this is what it looks like. So we have our abstract values that we operate over. So we have the minus, 0, and the positive. And we've also got these two new symbols that sort of actually turn our domain into a lattice. And as we've seen before, they're called top and bottom, hence the name of the talk, I guess. And they kind of mean, so before we said that they meant true or false. Now, when we talk about abstract interpretation, top means that we don't really know what the value is, and bottom is kind of representative of the uninitialized set. And so I guess this is where the power of abstract interpretation comes in, is because when we're operating and interpreting our code, we can always fall back to saying the value is top, in which case we don't actually know what it is anymore. And so, depending on how we design our domain, at the end of our interpretation, we could just say that all the values that we're interested in are top. And then, so is that really useful? Probably not. So this is kind of like the trade-off between designing a really simple domain like the sign domain and coming up with more complex domains. All right, so this is Lattice for the interval domain. And so, yeah, so it's kind of a bit different now, because before, with our sign domain, it was only 3 levels deep. Now we've got an infinitely high lattice that we have to work on. And this sort of causes issues later on when we get to loops and things like that. And so how this lattice is used is when we're executing and we reach a program fork and we go down multiple possible paths, and then those paths meet again, we use this lattice to sort of combine the results from those different paths when execution joins up again. So for example, down one path, maybe the value of a particular variable falls into this interval, and down another path, the value of a particular variable falls in this interval, and then so we use the lattice and we perform some operation on this lattice to say, well, actually, if the variable on one path is this, and the variable on the other path is that, then it must fall in this range, right? And so that's kind of how we use our lattice to abstract as we execute. And again, like we can always just fall back to saying, well, when the two paths join again, well, we just don't know what the final value is, so we go to top. All right, so that's the domain. The other thing we need is a function that takes us from concrete values into values in our domain. So that's this abstraction function. And so for the sign domain, if we have the empty set, we get bottom. If we have the value 10, when we convert it to our sign domain, we lose any information about what the actual value is, and we just know that it's positive. And similar here, 10 and 5, they're both positive, so we can represent these values as a positive value in our sign domain. When they're all negative, and when we have some combination of the two, we can't really say with any precision what those values are, because our domain only allows for positive, minus, or 0. So we just have to say, I don't know. And similarly with our intervals, the value 10 goes into this very simple interval. 10 and 5, now we know that our value is somewhere in this range. Likewise with our negatives. But now when we have a combination of positive and negative values, we can be a bit more precise because our domain allows us to be more precise because of the way that we've constructed our lattice. And so instead of saying, well, we don't know anything about this in our abstract domain for sign, we can say, well, the value will be between 5 and 10. So there's lots of values in that range, and we don't really know which one it is, but at least we have more information than just, I don't know. All right, and so the final thing that we need is some meaning to our program when it operates on our abstract values. So as an example, when we have the add instruction, we're no longer operating on integer values. We're only operating on whether the value is minus, 0, or plus. And so we can sort of work out from our basic rules of arithmetic what the final result of this addition will be. So, if we have two negative values, if we add them together, we'll still get a negative value. If we have a negative and a 0 value, we'll get a negative. But if we add a 0 and a positive value, we don't really know what the final result of that will be because it depends on the actual values, right? So the best we can do is say top, and I don't know. And so in our intervals, it's a bit simpler, I guess. Well, the table looks a bit simpler. And when we add two values but in these intervals, then it just becomes our lower bound is just the addition of the two lower bounds, and the upper bound is the likewise. All right, so this is our program from before that we did symbolic execution on, and now we'll do some abstract interpretation on it, I guess. So we start, we set everything, we initialize everything to bottom, so that's the empty set, uninitialized, and again, we'll treat this input variable as our input that we control, and maybe, we've done some other analysis of some other part of the code prior to reaching here, and it's already been set to, I don't know what the input value for in is. And so this is going to, as you can probably guess, this is going to cause problems because we're working on the really simple sign domain. So when we XOR all this together, we get 0 because that's one of the elements in our abstract domain. Similarly with R2. And now when we reach the branching point, we don't know anything about the path that we'll take, and so we'll explore both. So we'll split states and go down both paths. Again, we know that to go down this way, in has to be equal to 0, and to go down this way, in, we still don't know anything about it, so we can't be any more precise than top. And so we keep sort of running our interpreter over our two paths. This path doesn't really, we can't really get much more information out of this because, anything that we do on I don't know, the answer is still I don't know. So we can't really be any more precise here, but down this path, we can sort of, you'll see that, when we do this instruction, we're storing the value 10 to R2, and so R2 becomes the positive value. And again, we don't know anything about its actual value. We sort of throw this information away as we go. And so we keep going, and then we hit a point again here where we have to sort of take two different paths. Once again, we don't know anything about temp because it was based on the input value, which we didn't know anything about. And so now we have to explore both paths because we don't know anything about temp. So to go down this path, we do know that temp must be 0, so we can sort of reassign that as 0. And to go down this path, again, it's still just top. So we keep executing and we keep interpreting in our domain, and then we reach here, and now we've reached a point where we have to merge all these values in our table together. So this is where the lattice comes in, and we do this join operation on the lattice. And so what we do is we take each row in the lattice, in this table, and we sort of map it back onto the lattice, and we take a point above the lattice that accurately describes all these other values below it. So for the sign domain, I'll just go back. Where is it? So for the sign domain, the top row of our tables, we had some zeros and some pluses. The only thing we can do is move up to top when we do our join operation. If we were operating on a different domain, maybe this one, maybe we could be a bit more specific and move up to here or whatever, depending on what our values are. But unfortunately, we're stuck with a really simple abstraction, and so we can't really do much with that. Yeah, so this one here, R2, we can sort of do something with because we know they're all positive. So the result here will also always be positive, because no matter what path we take, R2 will be positive. But unfortunately, with in and temp, because we have this sort of diverse range of possible values, when we do our join on our lattice, we just end up with top. And then so here, when we add top in R1 with top in temp, we still get, I don't know. So what was the point in all that? Did we really learn much from this? I would argue probably not. We know that R2 is all positive at all points in the program. Is that useful? I don't know, probably not. And this sort of all comes down to how we design our domain that we're going to operate on. And this is really hard to do on binary code. So unlike symbolic execution engines, we can sort of go out and download a bunch of them from GitHub. If you were to look at an abstract interpretation engine on GitHub that did, I don't know, x86 or something like that, you wouldn't find much or anything, I would assume. Because, yeah, I guess when you're operating on binary code, you spend a lot of time ending up at top, basically. And this all comes down to accuracy versus cost of our lattice that we choose to use here. We can do something a bit more complex than our sign lattice, but the downside of that is that now when we talk about the semantics of an instruction set on these more complicated lattices, then we have to really think carefully about what each instruction does in our domain. So again, this example had no loops. When we get to loops, we have to do some other stuff that I won't go into here, but if people are interested, you can sort of Google for this stuff. You have to use what's called a widening operator. And yeah, I don't really want to say anything more about that. So the hard things with abstract interpretation is doing that initial design of your domain, and this really comes down to, well, what properties do you want to reason about in your code? If you care about, whether values or registers are positive or negative, sure, go and use the sign domain. If you want to, learn something maybe about buffer sizes, maybe something like an interval domain is more useful, because you can say, well, I have a buffer here, and its size is in this sort of interval. Maybe this is useful if you're doing vulnerability research stuff, because then you can sort of reason about overflowing buffers and that sort of thing. But yeah, it really comes down to what do you actually want to look for when you analyze your program. All right, so that's kind of it for abstract interpretation. And so I guess just to sum up the talk, I've kind of covered these three topics really superficially. And you saw that I didn't really talk about loops and more complex code constructs. But I guess my plan was just to give you an idea of what these techniques are and sort of point people away from this really disgusting academic literature that sort of describes things like abstract interpretation. I think that binary program analysis is sort of becoming popular again, and I think that's largely due to the DARPA challenge and all these symbolic execution tools that exist out there. But there's still a lot of work to go, especially at scaling up these sorts of tools and techniques onto real-world binaries, as opposed to the toy programs that they looked at in this challenge. So some of the important research questions, I think, is how do we handle this state space explosion? When we're reasoning about something like Adobe PDF Reader, there's lots and lots of possible states that our program can be in. So how do we reason about all of these, and how do we prioritize which states that we're actually interested in? How do we scale these techniques to look at these large binaries? So programs like Anger are written purely in Python, and so I kind of lurk on the Anger Slack, and one of the things that pops up a bit is people post, well, I tried to load Firefox executable in Anger to do symbolic execution in it, and my Python interpreter crashed, is a pretty common thing. So how do we scale these techniques to actually work with real programs like Firefox or Adobe PDF? And other than symbolic execution engines, yeah, there's not really a great deal out there in terms of open source. And yeah, so I guess that's it. Thanks for listening.
Incidentally, Adrian talked about things like CLE and Anger and S2E. Adrian is actually one of the developers of S2E, the symbolic execution engine, so that's great as well. So are there any questions?
Hey, so you've just given a great talk covering things like lattices and a few other concepts from abstract algebra, but you're kind of dismissive of the academic literature which kind of introduces these. So I'm wondering, if not from there, where would you suggest that we learn this kind of stuff?
Right, okay, so yeah, maybe I was overly dismissive. I don't mean to. I mean, I'm an academic nerd myself, right? So yeah, maybe my choice of language was not the greatest. However, I do think, in particular for abstract interpretation, the academic literature behind it is really difficult to understand. For things like symbolic execution and that sort of stuff, I think it's, yeah, the barrier to entry is a bit easier. But for abstract interpretation, yeah, I think a lot of the work that happens in academia is, and the papers that get published are very hard to digest. So where would you go instead? Yeah, I don't know. I guess if you really want to learn about it, then you sort of have to dive into all this lattice theory and all this kind of stuff that sort of helps you, gives you the background to understand these papers.
Question over here.
From a practical applied standpoint, what is the right size of application to analyze with the current tools? The right size, maybe like 1,000 lines of code or something.
Right. So yeah, that's a good question. I guess it depends on the tool itself. So for things like Anger and Manticore, those kinds of symbolic execution engines, when I read stuff about them and people writing blogs about them, they're mainly using them to solve CTF challenges and that kind of thing. So I guess looking at binaries of that type of size, and well, I guess I'm kind of biased because I'm the developer, or one of the developers of S2E, but I would argue that S2E can handle much more larger and more complex programs because unlike all the other symbolic execution tools, S2E runs on top of QEMU, so the emulator, and so it runs a full virtual machine, and so you can sort of reason about how your program interacts with its environment and the operating system, and you can't really do that with tools like Anger and Manticore and things like that because they're emulators written in Python, and when they make a syscall or call something in glibc, then it's harder to, you essentially have to write a model that emulates that functionality. And so if you've got code that does a lot of that kind of stuff, then yeah, I don't think you would get very far with tools like Anger and that.
Any more questions? Well, let's thank Adrian one more time.